Yes, my name is Jeff Probst, indeed. And I know there was two names on the presentation. We decided to split it up. My dad is Ken Probst. He's the other name that's on the presentation. He'll be going next session and talking about BGP. This session is about routing, and the two are made to go together. Hopefully, by going through this session first, we'll all have a little better understanding for the next one, which is the really harder of the two. And in fact, routing is really very quite simple, deceptively simple. So here's what we're going to talk about today. In order to talk about routing, we have to have at least a basic vocabulary of some pieces of IP. So we need to know a little bit of the functions. We need to know about subnetting, unfortunately. Once we get through a quick review, we'll actually go into an example. And we'll talk about the routing table, what it looks like, what's in it, and then walk through a routing decision. And then there's some other cleanup items on the far side. Again, this is all really simple, deceptively simple. I think we'll not have many problems with this. So before we begin, let's set some expectations on what we're here for. We want to take away the stigma that routing is hard, it's complicated, it can't be understood. None of those are true. Really, all routing is straightforward. It doesn't matter if we're talking about a laptop that you happen to throw up on your network, or if we're talking about an enormous 12-slot chassis router, the kinds of things like my dad sells. All of it is the same thing. Doesn't matter the scale. And hopefully, after going through this talk and my dad's talk afterwards, you'll have enough to be able to go further on some of these things that we are deliberately not going to cover today. There's a lot of depth in the topic, and we can easily get caught in the weeds. We're going to do our best to avoid that. To that end, there are some things we are not going to cover. We're not going to compare router brands. We're not going to have a holy war in this room. Let's just go ahead and get that out now. No holy war. We are completely vendor agnostic. In fact, I don't even mention any vendors here. We're not going to help you prep for your certification courses. You are not going to come here and then go be able to pass the CCNA. It's just not going to happen. Sorry, guys. We are demystifying a topic, and those certifications are getting into the guts of a topic. So we're going to be skimming across the top and peeling back the curtain on it. We're not going to have enough knowledge after this talk to be able to go take a certification. So don't come up to me and get angry in a couple weeks and go, I failed because of you. No, 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 no. We're also not going to talk about IP subnetting, which is intrinsic to routing, I recognize, but it's a whole lot of math and hangovers don't go together well. So we're not going to do that either. So we're just going to kind of walk our way around it. I think maybe not this year, but last year there was a talk on IP subnetting, and it's one of those third rail topics like regular expressions, which everybody knows they need and nobody really wants to learn. So we're just going to step around it. But we will have to touch in it because that's a part of routing. So with all those caveats out of the way, let's talk about IP. And this is a big, long text. I got this straight off of Wikipedia. I couldn't find a better place to go to than Wikipedia for this because this is succinct. The Internet Protocol is a principal communications protocol in the Internet suite. Yes, it is. For relaying datagrams, you could also insert the word packets across network boundaries. Its routing function enables internetworking and essentially establishes the internet. So just from this one little two-line sentence, or two-sentence paragraph, we can understand routing and internetworking are, what's the simpatico, I believe is the word. You can't have one without the other. All of IP is based upon routing. If you guys are familiar with the OSI model, it is layer 3. It is right above things like Ethernet, or from the old days, frame relay. More modern things. A lot of things are Ethernet these days. It is right below such other protocols like TCP, UDP, ICMP. All of those piggyback on top of IP. It is a connectionless protocol, which means every time an IP packet is routed, it is routed in isolation, and it is a best effort only. We are not forming a channel between two endpoints routing across a network. We're not prearranging anything. It is just at the moment in time, a packet arrives at a router, a decision is made, and that's that. So let's compare this to TCP, which is very clearly connection oriented. There, a channel is established. You have the SYN ACK, and they actually establish a connection. They have windows. They have to be communicating within a certain amount of time, keep alive, and all this very heavy minutia to keep the connection or the channel open. IP does none of that. So it's actually kind of an interesting dichotomy. IP, the lower layer, just makes the best effort to deliver, and TCP does its best to maintain a channel, knowing that IP can sometimes fail. So it's an interesting way of doing things. It's a very powerful way of doing things because you get both making sure your packets get there and it's fault tolerant. IP is very fault tolerant. So, like I said earlier, it is agnostic to happens at what layer 2. There is one caveat to that in the fact that we have to talk, we're actually not going to talk about this today, IP fragmentation. This is a case where your IP packet, which can be as many as 65K bytes, is too large to go into a single frame at layer 2. And so the router has to break up your packet into many individual frames. We call that fragmentation. At the other side, all the fragments have to be reassembled. So that is the only point at which we really care what happens at layer 2, and that's only because layer 2 gives us a number called an MTU. But I mentioned that just so you can go look it up later. So this is what an IP packet actually looks like, at least the headers. There's a whole bunch of information in here, and I'm going to zero us in on 3 particular items. Can you guys read what's on? Is it big enough? Okay. If you're following along, this is also online, so you can come back later on the website and check it out. I want to zero in on 3 particular items here. We're going to zero in on the time to live, the header checksum, and the destination address. These are the 3 things that the router is checking for every packet that comes through. And there are some other pieces that it may check. It may choose to look at the, this is labeled TOS ECN field for quality of service stuff. It's probably going to need to do some kind of fragmentation at some point, so the fragmentation offset comes into play. Those are all special cases. But for every routing decision, these 3 things are checked. The time to live is a bit of a misnomer. It's actually a hop count is a better way to put it. So when I send a packet across the internet, some measure of its reliability is how many hops does it have to go through to arrive at its endpoint. And we keep track of that with the time to live. For a packet that is expected to be reasonably short-lived, we may put a low time to live, like 10. And if it gets too many hops between where I'm supposed to be going and where I'm starting from, time to live may expire. And we'll talk about that later. Time to live is just a metric that we use as we're routing at every step. We also have a header checksum, for some reason buried in the middle of the header, not at the end. It's calculated over the entirety of the header, and this is how we know that the packet hasn't been garbled in transit. So the router, when it receives a packet, one of the first things it does is it quickly calculates a checksum of how it received. And the checksum fails, it says this packet is garbage, I don't know what to do with it. It just tosses it away. Again, this is connectionless. It's making no guarantees that your packet will get where it's supposed to be. Sir, a checksum of the IP header. So the question was, what is it a checksum of? Yes, so it's the IP headers, all the information in there. Okay. Is that better? Can I still be heard? I'll just talk really loud. I'm a loud guy in general. The third and probably the most important piece of information is this one towards the bottom of the diagram. It's the destination address. You have to know where you're sending your packet to. That one's pretty straightforward, I hope. So here's some example IPv4 and IPv6 addresses. I'm not really touching on the difference between the two here, but I wanted to make sure that we understand that the same routing decisions can be made on both packets in the same fashion. It's just that IPv6 is at a larger scale. IPv4 addresses are 4 bytes long. We've also heard the term dotted quad is a term for an IPv4 address, 4 bytes. An IPv6 address is 16 bytes, a lot. But the same exact principles, so if we go back to this here, an IPv6 header is going to have a lot more bytes for the destination and source addresses by necessity, and the header is slightly different. But still, these are the things we're looking for when we're routing packets. So we have to talk about the subnet mask. This is the last part of IP we have to get into. A subnet mask divides the IP address into a network portion and a host portion. And it's what allows us to make very quick routing decisions. So it's very common. You have a router in your home. You'll probably have a local network, 192.168.1. something. And so typically, our subnet mask in a home environment would be 255.255.255.0, like this. So we have a specific notation for this, a compact notation. In this case, I have used the IP address of the web server that I'm hosting the presentation on, for some reason. Just for the example, I have arbitrarily decided that the net mask is 255.255.255.0. That translates to a /24 on the end of the address. We're basically counting the number of binary ones in the net mask address. And this comes into play later on because when we're doing routing, we preferentially would choose routes that have longer net masks because they're more specific. And we would like to work our way from more specific to less specific. So in this example, the network portion, we apply the net mask to the IP address and we get 50.116.28. Those are the 3 bytes that will pop out. Now, it's important to note that just for our example here, we have used 3 bytes of ones as our net mask. We don't have to do that. It could be a /22, it could be a /18. This is the whole IP subnetting thing that we're not going to do the math on. Sir? No, it is not. It is just the address. The net mask is important to the interface at which it exists in, but while an IP packet is in transit, the net mask is meaningless. So it's solely for routing and logical partitioning of networks. So in this example, our host is number 118 on the 50.116.28 subnet. Like I said, for routing, we focus exclusively on the network portion, and we'll see an example of that here soon. So with all the IP review out of the way, we can get on to routing. And as I stated at the beginning, it's an intrinsic part of the IP protocol. You can't have one without the other. In fact, every single IP-based device that you own and operate has a router in it. So we're not just talking about the big routing tons of packets across the internet backbone kinds of thing. We're talking about every single device, every computer, tablet, phone, VM, anything that's IP packet based. Everything has a router in it. So maybe it's not so scary after all. If it's in everything, it can't be that complicated, right? And really, it's not, because quite simply, routing is just simply making a decision on where a packet should go to get to its destination. That's all it is. So we're going to use an example here of delivering a letter. It's a classic canonical example to explain routing. If I need to send a letter to my neighbor next door, I don't really need to use my mailbox for that. In fact, I can probably just go over, if I know the person, and knock on their door and introduce myself and hand them my letter. But then you might say, why don't you just tell them what you have to say? Anyway, just for our example, imagine that everything I have to say to my neighbor is in the letter. It has to be in the letter. That's the agreed upon format. Think of the letter as an IP packet. So I could just walk over there. I could walk down the street. I could walk across the neighborhood, a couple streets to my friend over there, but I really don't want to walk across town. That's a long walk. I've got too much to do. And there's a highway between there and here, and I don't really feel like crossing the highway. I'm not very good at Frogger. So I would rather use the U.S. Postal Service to deliver my letter across town. Great. Takes a day, gets there, they get my letter, fantastic. Would I prefer to use the US Postal Service if I have to send my letter to Japan? Now we're talking something different. It may take them 2 weeks to get my letter there. I mean, it'll get there, it's kind of slow. What happens if I need my letter there in 3 days? Well, I may choose to use a different service. I may choose to use UPS and their best service. Now, this costs me more money to do so. I can mail a letter for, what is it now, 46 cents? 48 cents? It's going up every year, something like that. I can send a letter for 46 cents. It's going to cost me $8 to overnight a letter to Japan. But side note, I think it's really cool we can overnight things to Japan. I've never had a need for that. I just think it's really cool that we're that connected. But for our example, we're going to make some analogies between our decision to use UPS versus the Postal Service versus walking to an analogy of IP. So the analogy is if I am talking to someone on my local subnet, that's as if they're in my neighborhood, and I'm going to walk over to them and give them my letter directly. I can do that. It's easy. It's local. That's the definition of the subnet. Everything within the subnet is considered like a neighborhood. For anything past that, I'm probably going to go need to talk to the router, and the router is going to have to do the packet delivery on my behalf. Now I made a decision to go with UPS for a longer range letter because they can get there faster. That's a routing decision. Both the USPS and UPS will get my letter there. One gets it there faster, and that's a routing decision that I just made to use one versus the other. So I hope that clarifies what we're doing when we decide, when we make our routing decision. I can explore this further. Is anybody unclear on what we just went over? Okay, good. I'm going to take the general lack of assent as okay. So let's talk about some facts about routing. There's a decision that happens for every single IP packet that passes through a router because IP is connectionless. At the time the packet is there and the routing decision is being made, we make the best possible decision we can at that point in time. Even if we had different information 5 minutes before, or we're about to get new information, we can't wait. We need to deliver the IP packet as quickly as possible, as efficiently as possible. That is always our goal in routing. So we make the decision we can at the moment in time that we have it. And since lots of packets are coming in all the time, we buffer them and we try to answer them in the order in which they are received. Now, in more modern times, we're doing quality of service. We may, at larger scales, choose to prioritize, say, voice traffic over something else because it's a little bit more latency sensitive. But for our example here, we're going to ignore quality of service. I only mention it so that you can go look it up later if you want. That's a rabbit hole. We could spend hours on that. So once a packet is forwarded by the router, it doesn't care what happens to it. It has a queue full of packets that it has to go through. So it literally is throwing it out the door in the direction it's supposed to go as fast as possible and getting on to the next packet over and over and over again. That's all it does. So let's look at a routing table. Boy, that ended up really tiny. I'm sorry. I pulled this routing table from the web server. I'm picking on my web server today. Web server where this site is, or this presentation is hosted. I have both the new flavor and the old flavor of invoking the routing table, so I don't offend anybody. But what I want to point out here is a very simple routing table. I have one device named ETH0, and I'm going to use the laser pointer. I recognize the video will not be able to pick this up. But right here you see dev ETH0. I have two different subnets, two different routes with subnet each. And that's because I have two addresses on this one interface, which makes it an interesting case study for us to look at. So as far as routing is concerned, they don't care how many IP addresses are listening on a particular interface. They don't care about any of that. They're only concerned with the network portion of this address, and they're concerned with the device that it should go out. So some, and we'll come back to some of the interesting information in here. But, well, the things we care the most about is the net mask, or the subnet, excuse me, the device, and I guess there's no metric listed here. If there's no metric, it's assumed 0. So there's a compact form. So you see in the second form down here, there's explicitly declared a metric here. This one is 100. These are 0. So those are the 3 pieces of information we need to make a key routing decision. The rest of this is window dressing and useful information for us. We're trying to interpret what the routing table is doing, but those are the 3 pieces of information we need the most. In fact, I think I have a slide about that right here. Here we go. Yes, the network address. We compare this against the packet destination's address. The metric, a positive integer representing the value of the route. And the device, which is the layer 2 device we need to be sending the packet out to. So this right here, this one slide, this is routing. Everything we've talked about is leading up to this one slide. This is all it is. It's 5 simple steps. The first 2 are just checking to make sure the packet is still valid. The first one checks that the checksum of the header and the payload is okay. If it's not, the packet obviously got garbled in communication and we need to throw it away. We check the TTL that I mentioned earlier. If it's greater than 1, we're fine. It means we can afford to send it on another hop. If not, we need to throw it away. Once we've done our little cleanup steps there, then we're going to compare the destination address against all the prefixes in our routing table, starting with the most specific. We're going to work our way down the routing table from most specific to least specific. We're hoping for a most specific route match. And we are using that assumption that clearly we need to do something special with that particular subnet. So a match, quite literally, is just using the net mask. Let's go back. Let's go back to here. Using this net mask here on the end of the address. Use that net mask on the destination address of the packet. If the resulting bits here match what you see after you've done that mask, then that's a match. It's very simple. It would also be helpful to write down the 1s and 0s sometimes. I'm opting not to do that here because we still have a lot to cover. So let's go back to where we were. So we find the closest match we can. If you recall from the table, we had 2 routes with the same length of net mask, I believe. They were both /24, I think. Maybe they weren't. Well, let's pretend that we had 2 routes that had the same length of net mask. So then if you have they both match for some reason, then you go to the next part, which is using the metric. So if we have 2 matching routes, then we compare the metric. We want the metric that is lower. We consider that to be a better route. And then once we've made the decision, this is the actual route I'm going to use for this packet, then we decrement the TTL in the packet. That forces us to recalculate the checksum on the header. We recalculate that, we write it in, then we send it on its merry way to the next stop. And that's it. That's all routing is right there. We've just talked about everything routing is, except one piece, and this is the piece that everybody gets hung up on, and that's the routing table. So, right, we really haven't touched on how did the values get into the routing table. And this is where the complex part of routing comes about. This is where everybody gets hung up. This is where you hear the big scary words like BGP, and it's really not that scary. He'll help you understand it. Or OSPF, or ISIS, which is the same thing as OSPF roughly, and just we have a different name for it. I don't know why. Or RIP, or all these different ways of filling our routing table. And sometimes we have automated routes, like from the operating system. That's what in the routing table that I showed you, those are all auto-populated. So when I give it an address with a subnet mask, it is assumed that everything inside that subnet belongs in the same neighborhood. And so there's an automatic route that's put into my routing table that says, if I'm trying to hit an address in that neighborhood, I can go ahead and deliver that letter. And here's the route to go do it. And here's the interface we need to go out. So the operating system does that for us. There are also static routes. I happen to know that this person lives at this spot and I have to walk down that road and then take a left to the light and go walk to the Jack in the Box, not get tacos, take a right there and go to his house. That's a static route. And there's no tacos involved in static routes. There are also dynamic routes, which are usually populated by your routing protocol of choice. For a very small setup like your laptop on a local area network at home, you don't need a routing protocol. If you're talking an ISP, you probably need a routing protocol of some kind. And depending on what you have, you may make a choice on one routing protocol versus another. We are not going to touch on that because that is yet another holy war, and we're just not interested in that. I do mention, though, these are things that you can go study further, and you will probably lose some hair in learning some of these things. If we boil them down, like BGP will be boiled down, they're easier to understand, but there's still a lot of intrinsic knowledge one has to know to understand how the routing protocols work. But we can set all that aside and kind of say, we'll deal with that later. The net result of those routing protocols is to populate our routing table. Once the routing table is populated, we can make our routing decisions and go on our merry way. So we're not going to touch those today. We're just trying to demystify the topic. So there's very commonly a gateway route, also called the route of last resort. So you saw it in the routing table. It was labeled default. So this route says, if I don't know where to send a packet, I'm going to send it to this route instead. So if you're sitting at home and you're looking at your home network, this would be your ISP, like Verizon Fios, or God bless you if you have this, Comcast or something like that. Those are your ISPs. If you don't know where to route it, and you have a very small network in your home, so odds are all of your packets are going to be going out. You're going to hand it to your gateway with the assumption that the gateway knows what it's doing. That may or may not be a good assumption, but in IP, every routing decision is connectionless and standalone. So we make the assumption that, oh, that's my gateway. I can just go hand the packet to that person and he can handle it. This is equivalent to handing your letter to the postman. I don't know what it takes to get a letter to Minnesota, but they do, so I hand it to them. Usually we give it a very high metric. If you recall from the diagram, the default route had a metric of 100, and the other routes had metrics of 0. So we only land on the gateway route. If you also saw, the net mask for the gateway route is 0. So it will be matched last no matter what you do, and it has the highest metric. So it's literally the very last route you will ever get to. So any packets not matching the other routes are sent to the gateway. Now, there are some situations where you won't have a gateway route, like your ISP is down. I feel bad for you if your ISP is down. But at that point, your gateway route may disappear because the assumption that you have somewhere to send your packet is no longer valid. You're disconnected from your ISP. Or you're in an embedded setup, or you're in a zero conf LAN or something like that, then you may not have a gateway. But almost every situation you'll find yourself in, you're going to have a gateway route, except when you're talking about the really biggest ISPs. What we find is that our gateway routes end up building a tree. So I have Verizon Fios as my ISP. My gateway points at them. They have a gateway that points at somebody larger. Actually, are they one of the big tier ones? Okay, so Verizon probably handles my traffic for me. But if I'm a small local ISP, or if I'm using, like a small wireless ISP like Clear, they're not a big high tier ISP. So they are they're clients of a yet larger ISP. So my packet would go to them. They have a gateway route up to their ISP, and so on until we get to the backbone. Up at the backbone layer, which is where BGP reigns supreme, you don't generally have a gateway route because you know where everything generally should go. And again, we're going to cover that in the next hour. So what this forms into is a tree structure, and we call this tiering. It's not a hard and fast rule like We just learned that Verizon can route my packet entirely by itself. It doesn't need tiering to figure out where to send it. But in general, most of our ISPs, most of our network experience are going to go through some level of tiering. And then, again, that's going to be covered in the BGP talk. So there we go. Okay, so all the stuff we talked about, we've largely covered routing, and it just kind of seems too easy. Like, I thought there was more. When I first started studying this in depth, because I thought, oh gosh, think about all the stuff I'm going to have to put in this presentation. It's really not. This is routing distilled. This is all routing is. That's all there is to it. It's not difficult. It's not complicated. It's just a couple things you need to remember. But there are some gotchas. So the routing protocols we talked about, those are very complicated. The ways and methods that they decide how should we fill the routing table, what are our metrics, they're adding things, they've got to talk to other servers and other routers, and so they have very complicated orchestrated dance to get all of them working together. Those are complicated. But if you think just about the routing table itself, it's very simple. What order should I do my route comparisons for the highest efficiency? We said we started with the longest subnet mask for our comparison. Well, what if we know that the longest subnet mask is a route that's going to be used infrequently? So we may want to break that paradigm and instead compare a couple other routes first. So that way we're not always making a comparison that we know 99 times out of 100 is going to fail. So there are some complications. You can adjust the order in which your routes are compared. You can make that adjustment with your metric. You can actually go monkey with your routing table. Some of the protocols will do that. So there's some complication there. Again, we're trying to seek a highly efficient router. How fast can I go? So I have a routing table. I'm assuming it's in memory somewhere. What can I do to make this faster? So we're talking about a big boy router running many megabits or gigabits of traffic running through it. We want to make our comparisons as efficiently and as quickly as possible. We have a lot of traffic to get through. So we're going to do things like look-aside buffers, and we're going to do, as the packet is coming in, it used to be you would wait for the entire packet to come in, and then you would do your work on it. But as the packet is coming in, before we even calculate the checksum, let's go ahead and start comparing the routing table over here, and then we'll do the checksum over here. So hopefully by the time both of those are done, it'll be faster, as opposed to doing the checksum and then the lookup. So there's things that can be done on a big boy router scale to help things go faster that we're probably not going to run into on our small scale. But these add complication into the routing decision. If you take all of that away, routing is just this simple. You can just build pieces on. And that's really all we have to talk about to demystify routers. So does anybody have any questions? Yes, sir. So the question was, packets are dropped if there's an error, and what role does ICMP play in all of this? So ICMP is a layer 4 protocol. It sits on top of IP, and the goal is if something systemic is happening, then we want to send messages back to the source that, hey, your packet was garbled. You're probably going to need to resend this. Or flow congestion. Hey, things are way too congested for me to send your packet right now. Sorry, you got selected for reaping. So this is the role ICMP plays. It's purely a messaging, I don't know what the C stands for. The MP is messaging protocol. It's basically for connection and flow control. So everybody probably has heard of the ping, and that's just a simple flow control mechanism to make sure that the path between me and there is clear and we can reach it. And that's all it is. So that's the role ICMP plays. Yes, thank you for reminding me about that. So the question was, is there some standard, some requirements of the standard for ICMP? The two that he mentioned was destination reachable, time exceeded. And again, time to live and time exceeded is kind of a misnomer. It's more like hop count exceeded. But both of those are messages. If your TTL dies, if you run out of TTL, then the router at which you ran out of TTL will send a message back to the source to say, hey, you ran out, time exceeded. And it's a specific ICMP message with a specific format with a little bit of information in it. Likewise, if there's no way, so let's say you're at home and your connection to your ISP dies, then your local computer, which has the router in it, is going to try and reach google.com, and it can't. And so it's going to return to you, hey, I can't possibly get to where you're telling me. I don't have a route to get there. My gateway's down. Nothing's working. So it would return an ICMP destination unreachable. It's really infuriating when that happens. But yes. Are there other questions? Yes, sir. So more of a statement, a suggestion, I guess. Talking about a laptop that has multiple interfaces on it, or a device that has multiple interfaces on it, and how that would come into the routing decision. Well, let's say that both of them are connected to a way out. We call that multi-homing in a simple setup like this. And that starts getting into some of the more complicated things. What you would do in routing is one of those would be considered the better of the two, even if they're technically equal. I think my personal preference is the wired connection is better than the wireless. There's going to be some latency, and let's say the guy next door is making nachos and your packets are going to be dropped in the wireless. So we prefer the wired connection. So we're going to say we have two valid routes out of our network here. The wired connection is going to have a lower metric. So if the wired connection is working, and even though they have the same subnet mask and the same route and everything, the metric is lower for the wired. So we're going to preferentially select the wired connection over the wireless. And if someone steps on my cable and breaks it, or the cat yanks it out or something, I don't know what's going on. If the wired connection disappears for any reason, we still have the wireless connection. So as the wired connection gets lost, the system will update and say, hey, that's no longer my routing table. I'm going to delete that route. And so the route is gone. Now we have the wireless connection. Yes, it has a higher metric than what the wired connection was, but with the wired route gone, then the wireless route wins because there's nothing competing against it as far as the metric goes. This is a simple, like a laptop style case. We're talking on a bigger router, like your office, is very likely that you have more than one ISP. Now you start getting into some of the hairier decisions on, well, both of them, I have like a 3 megabit backup pipe to this ISP over here, and then I have my main 30 megabit over here. I would preferentially send all of my packets this way. But if that goes down, then I can use this. And that's a pretty easy decision to make. Let's say you have two relatively equal 30 megabit pipes, and you want to use both of them. Now you're starting to get into something that's, let's say that it's a little bit outside the scale of routing. We would make, in that such a case where we don't care which of the two, so like a load balanced ISP connection, we would create an equivalence class whereby the two routes are combined into one. The decision is made to go that way, and then something after the routing decision is made will decide which of the two links happens. I think there's software built into Linux called is it Zebra, I think, that does that? And you can do equivalence classes on routes. That's getting really advanced stuff. But it's all possible. It's not technically part of the base routing element, but it's something more of a system level thing. So. Any other questions? Yes, sir. Mm-hmm. So the question is, when I run Traceroute, what is actually going on so I can see all the hops? What it's doing is it sends a series of ICMP pings to every hop in the chain. And it starts off the first with a TTL set to 1. And then the second packet it sets with a TTL set to 2. The third packet TTL set to 3. And the idea is, as long as the channel that is formed, please forgive the usage of the channel that is formed between you and your destination is reasonably static, you're probably going to get the same routers in the chain all the way along. Allows you to map every single step in your way, all the way until you get to your endpoint, which may be 3 hops away, 10 hops away, or whatever. But it's sending those series, and then you might do that over time with something like MTR. So once you have all that information collected, you can work on it. But it's using the TTL mechanism. Any other questions? Sure. A statement that's true. The statement was that Traceroute uh, can be useless because, well, for many reasons. You're saying specifically, it increments the port number it's using for every time it's sending it out. So you're blasting through, and this is, now we're talking about a layer above IP here. We're talking, I think, if it's ICMP, there's no port number involved, isn't there? Yeah. So right, and that's the traceroute is just a series of ICMP packets. Hmm. Okay. So he says that a lot of the ISPs are denying traceroute, or we think of traceroute, or I'm sorry, ICMP traffic is less quality than other traffic. If I've got music streaming and a download and all this stuff going on, and I'm struggling to keep up with all this, I'm going to ignore the guy who's just asking for a ping. Screw that guy. We don't need it. It's less valuable data, and I'll deal with it when I can. So there are times when you're doing your traceroute, if you're doing an MTR, you're measuring what your packet loss is over time, and you keep seeing a consistent amount of packet loss at a particular router. It could mean the router is congested and is not able to handle your ICMP request, or it could mean that the router says, screw you, we're not going to handle you right now. So, and that's, you don't know the routers you're going to use on the route between you and your endpoint, and that's just whoever's maintaining the router may make a choice like that. Okay. Apparently, I don't fully understand traceroute. Then I thought I did. I thought it was just purely ICMP. Um, so I have some reading to do. So, question. Okay, so that's what I'm misunderstanding. Okay. Okay. So there's multiple versions of traceroute is what he's saying. Well, some with UDP, some TCP, depending on what you end up with. It's implemented differently with different operating systems, I assume. So, right. Question in the back. Correct? We can't modify that. The question is, if IP is connectionless, how does it impact us when we're doing like a VPN or something like that? So the VPN, what it's doing on the fly, it's adding some routes into your routing table such that we know, so it's usually two parts. The VPN is setting up a new device, a virtual device for sending our network traffic. It's usually a user space device. And it's adding routes to the routing table such that all traffic designed for these IPs should go over this new virtual device. That's VPN in a nutshell right there. So still, it's connectionless. There's no guarantee that it's going to survive, especially since usually it's a user space device, and it may be tied up in the processor somewhere. You still have no promise that your packets are going to get where they're supposed to go. But the routing decision, as long as the routing table is being cultivated properly by the VPN client, then it should arrive where it's supposed to, and all the normal rules apply. Does that answer your question? The question is, can I have multiple routes in a VPN? And the answer is absolutely. Whatever VPN you're using, it's wherever you connect into, that determines what alterations are going to happen to your routing table. And it's entirely implementation specific. So it's quite common that a company will deliver VPN clients to their workers that have the routes baked into the software. And they know this is this IP space we're using inside our company network. Here's what you're going to need. There's also Depending on the VPN solution you use, you could negotiate for the rates. It could be told to you by the server at the time in which you're negotiating for the VPN connection. Those routes will be relayed down to you. The net result is it's really hard to know ahead of time what your VPN is going to do unless you know what you're VPNing into explicitly. So, we have any other questions? Yes, sir. So the question was, if you have two interfaces with the same subnet, how can I specify I want some traffic to go to one and some traffic to go to the other? Are you subdividing the subnet? You could do that. You could say, let's say it's a /24. Everything in this half of the /24, we're going to modify a routing table, and all this half should go there, and that half should go there. Or you could do something a little more complicated, like what we were talking, the multi-homing example, where you create an equivalence class for both of those devices, and then something after the routing decision to go to that virtual or equivalence class device, something decides which of the two. I think it's QABBA. That's what it is. And Linux has this service. I don't know how to say it. Quaba, Kaba. I don't know what it is. But it actually can handle multi-homing using this service. And we do that. The routing decision has to go to a particular device. We can invent devices on the fly if we need to. And so we just invent a new device for this particular use case, and that's how we handle it. So, any other questions? Sir? The cookies that I was bringing to him. The question is, what is the guy next door looking at? I brought him cookies. Oh, he was making nachos. So microwaves, the microwaves are in the 5 gigahertz band, in the same place as where all of our wireless internet is. And so when the guy next door starts microwaving his nachos, I lose my my gameplay. It just boop, it goes bye-bye. This actually happens quite frequently when I'm watching a movie. It's really irritating. And so when we're watching a movie, I comment to my wife, hey, the guy next door is making nachos. So teenagers, excuse me. Yeah, they're very hungry, and they're young, strapping lads. They're probably eating lots of nachos or popcorn. Anyway, any other questions? All right, guys. Well, thank you very much for hanging out with me. I hope we demystified routing for you guys. Stick around for BGP. It's coming up immediately after this session.
Citrix XenServer gives you everything you need to integrate, manage, and automate a virtual data center, all on an enterprise-class, cloud-proven virtual platform, and at a third of the cost of other solutions. But why even bother with virtualizing your server infrastructure in the first place? Well, let's say you have a traditional one server to one application architecture, but you're running out of resources and performance is suffering. Once you order new server hardware, you'll wait for delivery. Configure it, install your business application, stage and test the server, and finally, add it to your production farm. If you've been through this process before, you know it can take weeks or even months. You also know it's a manually intensive process that will burden your team every time you outgrow your current setup. With a virtual server solution, you could accomplish all of that in less than half a day.
Your customers rely on your website or application. If it's slow or non-responsive, it infuriates your users and costs you money. Keeping your business-critical systems humming along requires insight into what they're doing. Your system metrics tell stories that can reveal performance bottlenecks, resource limitations, and other problems. But how do you keep an eye on all of your system's performance metrics in real time and record this data for later analysis? Enter LongView, the new way to see what's really going on under the hood. The LongView dashboard lets you visualize the status of all your systems, providing you with a bird's-eye view of your entire fleet. You can sort by CPU, memory, swap, processes load, and network usage. Click a specific system to access its individual dashboard, then click and drag to zoom in on choke points and get more detail. Comprehensive network data, including inbound and outbound traffic, is available on the Network tab, and disk writes and free space on the Disks tab, while the Process Explorer displays usage statistics for individual processes. The System Info tab shows listening services, active connections, and available updates. Adding LongView to a system is easy. Just click the button, copy the one-line installation command, then run the command on your Linux system to complete the process. The agent will begin collecting data and sending it to LongView. Then the graphs start rolling. Use LongView to gain visibility into your servers, so when your website or app heats up, it stays up.
Citrix XenServer gives you everything you need to integrate, manage, and automate a virtual data center, all on an enterprise-class, cloud-proven virtual platform, and at a third of the cost of other solutions. But why even bother with virtualizing your server infrastructure in the first place? Well, let's say you have a traditional one-server-to-one application architecture, but you're running out of resources and performance is suffering. Once you order new server hardware, you'll wait for delivery, configure it, install your business application, stage and test the server, and finally, add it to your production farm. If you've been through this process before, you know it can take weeks or even months. You also know it's a manually intensive process that will burden your team every time you outgrow your current setup. With a virtual server solution, you could accomplish all of that in less than half a day. Server virtualization software separates the OS and application from the underlying server hardware. And with multiple virtual machines on a single server, you can use each of them to run different OSs and applications. This makes it possible to move your virtual machines from one piece of hardware to another whenever you want, to maximize utilization, simplify maintenance, or recover from a hardware failure, and without slowing down your applications or users. Clearly, server virtualization provides big benefits, and Citrix XenServer provides even more. Since it's built on an open platform, XenServer plays well with your existing hardware, storage systems, and IT management software, as well as with the industry's leading cloud service providers. Best of all, you can get started by downloading a fully functional, production-ready version of XenServer for free. After a 10-minute installation process, you'll see how easy it is to start virtualizing your workloads and automating your IT management processes. And when you're ready for a richer set of management tools, just upgrade to one of the premium editions of XenServer. So whether you're interested in virtualizing servers for the first time, expanding your server virtualization footprint, or moving server workloads to the cloud, download and install XenServer today and see how it can help you simplify your IT environment. Citrix XenServer. Do more. Don't spend more.